Assalamu alaikum. So, in today's lecture, we're going to look at some transport properties particularly for metals in which there are free electrons. So, we'll have two lectures on the transport properties, one today and one the next one, before we move on to the band structure. So, however, if you would just like to wrap up our discussion from yesterday, we did derive the energy for the free electrons in the presence of a magnetic field due to Landau diamagnetism or Landau quantization. So, the energy in the presence of a magnetic field had some additional terms over and above the energy in the absence of a magnetic field. And this energy were 8/5, the density of states at the native Fermi energy alpha, which is 0.105 mu. Let's talk about this mu later. 2/5 EF square DEF alpha over x naught square plus 2/5 EF squared DEF alpha beta x naught raised to power 5/2 and oscillations of constant magnitude. Right, so does this tally with your result from yesterday? Now this is the total energy in the presence of a magnetic field. This is the energy in the absence. And these two additional terms appear. One is without the oscillations and one has the oscillations in it. ये लिखा नहीं आपने कल? हमने पूरा नहीं ना लिखा इसके। नहीं ऐसे नहीं हो सकता।
नोट के टर्म्स नहीं आ रहे नोट के टर्म्स नहीं आ रहे।
अच्छा फिर यू नॉट को मैंने खोल दिया ना,
तो फिर वो भी नहीं खोलेगा बाय डेफिनेशन।
खोलना चाहो तो खोल दो। देखो ना यू नॉट को, इस यू नॉट को ओपन अप कर सकते हैं ना आप।
ठीक है।
Where, so I can also write down u naught, where u naught is two over 3, 2/5 EF squared DEF right. So this is u naught. So this is u naught and this much is u naught. Now does it match your what you've written on your notebooks? All right. So this is where we finished our previous lecture. Now if you observe here, in the presence of a magnetic field you have electrons and they're inside a magnetic field. The energy changes, it's no longer u naught, but we have these additional terms. This third term on the right hand side has oscillations in it. where this period is, if I plot this with respect to x naught, this period is 1. Okay, and alpha is 0.105, beta is almost 0.3. And where does magnetic field appear inside this relationship? X naught. So x naught has magnetic field in it, h bar EF over h bar omega c. EF h bar omega c is EB over m. So this is my x naught. So now I can insert these values of x naughts into the expression for the energy, and I can write down the energy in terms of the magnetic field. So this is an oscillatory term. If the temperature is large, these oscillations don't show up. And only this term survives. So if you really want to see these oscillations, the temperature of the system has to be lowered, or the magnetic field has to be increased. Observe that x naught is in the denominator, so the magnetic field will be in the numerator here. So in order to see this effect, you really need to have very large fields. And the condition is that h bar omega c is proportional to the magnetic field, must be much larger than the thermal energy. So Landau quantization, this term appears because of Landau quantization. All the periodicity, the oscillations, are a result of Landau quantization, and it shows up in this particular term. So if you want to see this effect, the spacing between the Landau levels, h bar omega c, this is the spacing, h bar omega c. This must be much larger than the temperature. If the temperature is larger than h bar omega c, then these levels will be almost degenerate, which means that all of these levels will be populated and the electrons will not be able to tell that quantization exists. So if you want selective population in some of the Landau levels, you really want to have these gaps, they must be much larger, so that thermal disturbances cannot excite the electrons from one level to another. Okay, so quantization shows up only when the field is large. So this term shows up when the field is large or the temperature is small. It is in this regime that the quantization appears. And when this happens, you will see oscillations in any quantity that is derived from the energy. Okay, at high temperatures, this term survives, and this term just vanishes off to a small number. The oscillations die down. Okay, you don't see this term. This term overwhelms this term here. Okay, so if I were to and it's immediately obvious because there is x raised to power 2 here and x raised to power 2.5 here. So this term by default is smaller than this term. Okay. Now if I were to look at this expression at high temperature, which means that h bar omega c is smaller than kBt, then I can only consider the first or the second term on the right hand side. Now suppose I want to calculate the magnetization for this system of electrons. The magnetization we know is given by the derivative of the magnetic field of the energy with respect to the magnetic field. This is how we define magnetization. Once we know the energy, we take the derivative with respect to the field, we can find the magnetization. Okay, so let's find out the magnetization for the system of electrons. So in the high temperature regime, UB is U naught plus 2 over 5 EF squared DEF alpha X naught squared, which is now E squared H bar squared capital B squared EF squared M squared. Correct? So I can cancel out the EF squares, EFs, and this term EH bar over 2M has a special name. It's a fundamental constant. What is this fundamental constant equal to? नहीं वो तो E और H होता है. This is the Bohr magneton, mu b, the unit of magnetic moment. So EH bar over M is 2 mu b. And so this EH bar and M appears here. So this becomes 4 mu b squared. So I will get U naught plus 2 over 5 4 DEF alpha mu b squared b squared. So I get 8 over 5. This becomes 8 over 5. Okay, so let's take the derivative of this energy with respect to B, put a negative sign with it. I get minus 16 over 5 DEF alpha. I just put this equal to the numerical value that we found from our previous lecture, 1 over 3.3 mu b square b. Okay, so we also know that this density of states is 3 over 2 n over EF, correct, by definition. So this becomes minus 16 over 5 1 over 3 mu b square b. So this 3 is just alpha, sorry, alpha is not 1 over 3, it's 0.105, sorry, 0.105. Sorry, it's not 1 over 3, it's 0.105. Beta is 1 over 3. So this becomes minus 1 over 2 था, right? ठीक है, ठीक है. और alpha ये था. Okay, 48 into 0.105 divided by 10 n. Instead of EF, let me write KB, Fermi temperature TF, mu B square. So instead of B, let me write mu naught H. So this is my magnetization. From this magnetization, can I tell what the susceptibility is, Kai? The magnetic susceptibility. Right, so this is just this, m is chi h. So this is just this coefficient, this is chi, this susceptibility. So this turns out to be, so if you kind of work this out, this is 4.8 into 0.1 is about 0.5. 4.8 into 0.1 is about 0.5, roughly minus 1/2 n mu naught mu b square kb Tf. So this is the paramagnetic susceptibility due to Landau quantization. Now when we had free electrons inside the system, we also had a paramagnetic term which came out purely because of the Zeeman effect. That was called polyparamagnetism, and that was paramagnetism. It had a positive sign, and that expression turned out to be x poly was plus 3/2 n mu naught mu b square kbTf. Probably I'll ask this in your final exam as well. I would ask you to derive this. So this is polyparamagnetism. Now you observe that the diamagnetic effect, the minus sign shows it's a diamagnetic effect, which means you apply a magnetic field in a particular direction and this swarm of electrons gives a magnetization in the opposite direction. This is diamagnetism. So the diamagnetism resulting from the magnetic field, which is called Landau diamagnetism, has a susceptibility which is 1/3 the susceptibility of the polyparamagnetic effect. Okay, so this diamagnetic effect is 33% as strong as the polyparamagnetic effect, and it's diamagnetic. So the overall susceptibility will be a sum of this poly term and this Landau diamagnetic term. Overall, these electrons will show paramagnetic behavior because this term is 3 times stronger than this term. So now you have electrons inside the solid, free electrons. They're not interacting with one another, but they do respond to magnetic fields. They show magnetism. Okay? And at the moment, we're not talking about any spins that are associated, latched onto the ions. So we're not considering any paramagnetic ions like copper or manganese. We're just talking about free electrons that might exist inside a metal. If you lower the temperature and still have large fields, you will also see oscillations in the magnetization. So if I did not truncate this to the second term, I included a third term, I will see oscillatory behavior in the magnetization. So very sensitive experiments which are done at really millikelvin or sub-Kelvin temperatures and large fields, they do show these oscillations, which are called, as I mentioned yesterday, Van Alphen de Haas oscillations. The resistivity also shows oscillations because the density of states has this periodic form, and as the density of states, as the peak of the density of states passes through the Fermi level, a spike in the conductivity appears. So the conductivity also shows oscillations in the presence of a magnetic field, and I'll upload some research articles and some diagrams taken from research articles on the web page to show you real results from these magneto-oscillatory phenomena. Okay? Question? ये वाली, ये तो हमने एक पिछले लेक्चर में डिराइव की थी. तो so this polyparamagnetic term is derived by looking at the density of states in the absence of a magnetic field. So this is my energy, this is the density of states, this is the Fermi energy, and then in the presence of a magnetic field, the spin up band, which is pointing parallel to the magnetic field, is lowered in energy, and the spin down band, which is opposite to the magnetic field, raises its energy. So these electrons over here see some vacant levels in the vicinity of this Fermi energy. They kind of drop down, and overall the final density of states diagram that is achieved looks something like this, which means that there are more electrons with spins pointing in a particular direction than in another direction. And using the Sommerfeld theory, we derived the difference in these populations. That difference in population, since each electron has a spin mu b, you take that difference in populations, n plus minus n minus, you multiply this with mu b. This will give you the magnetization. And then you do this, mu naught, you divide this by h, you'll get the susceptibility. This is how you derive this relationship. So when we, during our lecture on the Sommerfeld expansion, we did derive the polyparamagnetism. So these electrons have paramagnetism as well as diamagnetism. So this concludes our discussion on magnetic field effects. Now let's come to more commonly investigated transport properties such as electrical conductivity and thermal conductivity. So these are the experiments that probably an undergraduate student is likely to do in a laboratory. Measure the conductivity or resistivity of something. Right? So any questions up till this point about the magnetic effects? Still we are inside free electrons. Remember, we're looking at electrons, they are non-interacting, they see this positive sea of ions which is homogeneous. Sometimes this is called the Jellium model, and we have the only quantum effect that we've introduced is the Fermi-Dirac statistics, which comes out from the Pauli exclusion principle. So we know that these electrons obey the Fermi-Dirac statistics. They have a particular quantized structure in the K space. Levels up till the Fermi sphere are filled and so on. And you've seen multiple times that density of states at the Fermi level is very important in the computation of these properties. Okay? So now let's move on to considering some transport properties. In particular, let's start with how conduction happens in the purely classical model, in which we just see the electrons. We do not consider any Fermi-Dirac statistics, any Pauli exclusion principle, just the electrons are a gas of electrons, a gas of particles. Okay? So we want to look at a purely classical model first and treat these electrons as if they were gas atoms, gaseous atoms. So we want to use the kinetic theory of gases to look at the properties of these electrons. Okay, so we're going a step backward from our quantum model. And this is something that you might have already seen. The overall picture, let's call it the Drude model. So in this model, what we really have is, suppose this is an electron inside a metal. It's moving with a certain velocity, v, and there's no electric field applied onto this metal at the moment. So what this electron does is that it sees some object, some interaction that scatters it. To see another electron, it could see an ion, and it just scattered. So with time it's doing a random walk, and this velocity is, as we all know, proportional to the temperature. So the equipartition theorem states that this energy, half mv squared, will be proportional to the temperature of the solid. Okay? So along each dimension, the half mvx square will be proportional to kbt over 2 along each direction. That's the equipartition of energy theorem, in which each degree of freedom holds the same amount of energy, and there's no potential energy for the electrons. So the total energy for the electrons is equally distributed along the x, y, and z directions. So in any case, the overall velocity of any electron with time gives you 0. So you average the velocity of any electron over time, you get 0 because of this random motion. Agreed? So this is one electron. If you have a large number of electrons and you average over the ensemble, so if I average over the number of electrons, I still get 0. So an ensemble average is the same as the time dependent average. So this is called the ergodic hypothesis. This is ergodicity. Okay, so it's a stationary process. It's a totally random process, a normal random process. Now, what happens is I can also write a Newton's equation for the motion for these electrons, right? So m dv by dt is going to be equal to the force that the electron sees. No force, this is 0. But then you have to take into account the scattering. So if there is no scattering, this term will be equal to 0 and the velocity will be constant. But we know that there is scattering. Okay, so let's write down an equation that introduces both a force and a scattering. And it's a classical equation. So the force is, suppose I apply a force which is as a result of an electric field. So what is the force due to electric field? E is electric field. What is the force due to the electric field on an electron? So charge is minus E. Now this is electric field. Suppose I also apply a magnetic field. So minus E V cross B. Okay, so this is generally called the Lorentz force, electric field. And then let's also take into account scattering. So one model for scattering, the Drude model, is simply the scattering can be modeled as a frictional force which damps the velocity. So I can write this as minus V over a scattering time tau. So tau is a scattering time, it's the average time between collisions. Okay, so this is a classical equation in the Drude model, classical model that might describe the motion of an electron. Yes, please.
minus V upon tau वाला term है, किस अगली interaction कौन से आ रही है?
First of all, in this classical equation, this is a phenomenological term, which means that the electron which is being scattered, it moves a certain distance L and then is scattered. Now there's a distribution of L's and there's a distribution of times about which this is scattered. So if I make a plot of the time interval T between scattering events and write here the probability for those time intervals, it peaks at a certain value. Generally this is a Gaussian. This peak value is called tau. It's the average value of free motion of the electron. Okay, so it's an average time over which collisions take place. Now where does this come from? The classical model says that it's coming from what could happen. The electron is colliding with other electrons. That's one mechanism. classically, if you think of it. If you just look at the particular corpuscular nature of electrons, it's colliding with other electrons. The other is that it's colliding with the ions. But the ions are also vibrating about their fixed positions, and higher the temperature, higher will be the cross section of vibration. So the electron is probably interacting with itself, and it's definitely interacting with the ions. So those two mechanisms, they can be lumped together into this model. Okay? Now when we look at this model from the perspective of the Fermi sea of electrons, we can describe these scattering events as interactions between an electron and another electron, an electron and phonons. So there are two contributors to this relaxation mechanism: electron-electron interactions and electron-phonon interactions. And it happens that the electron-electron interactions are very difficult, because I will explain in the next lecture why. So it's primarily due to electron-phonon interactions, two particles colliding with one another. So what can happen is, if we go a little bit further than what I had, with a certain wave vector ki, it can absorb a phonon. The phonon has a wave vector q. So an electron can absorb a phonon, and the scattered electron kf has a vector kf, and this kind of interaction takes place. The momentum has to be conserved, and the energy of the electron plus the energy of the phonon must equal to the final energy of the electron. So both momentum and energy have to be conserved. So either the electron can absorb a phonon, this is how a two-body collision takes place of two quasi-particles, or what can happen is that this electron is interacting with the crystal structure and it emits a phonon. And in such a case, this is the momentum conservation that takes place, and the same energy conservation is happening. So electrons are interacting with phonons. But in the classical model, there are no electrons, there are no quasi-particles, there are no phonons, they are just scattering events. So irrespective of the mechanism, this is a phenomenological model. So let's see how this model works. So first of all, what we do see is, I would first of all like to ask about this velocity v. Now I've applied an electric field. This is my solid. Suppose this is the direction of my electric field, E. Now I have an electron. What would be the direction of the force on the electron? Opposite to the field, because it's a negatively charged particle, right? Generally like this, right? But it's also, this electron is also showing random thermal motion because of the temperature T, and that random thermal motion is in a random direction. So overall, these electrons are going in random directions, but due to the imposition of an electric field, the sum of all of these V's for all the electrons is no longer zero. There is a slight nudge towards the right. So there is some resultant velocity. Let's call that velocity Vd. It's called a drift velocity. Drift velocity. Now, between scattering events, the electron is really showing random thermal motion. The speeds are very large. Okay? They could be, say, in meters per second, or probably tens of meters per second. But this random drift velocity could be very small, and we can determine what this drift velocity is. So this is a directed velocity, non-random part inside the overall motion. So any electron is showing both the thermal velocity, so between collisions it's moving with the thermal velocity, and then it's scattered, goes off in another direction. But overall, when you observe this electron over long periods of time, you see that this electron is moving with a small drift velocity, which is unbalanced. And this drift velocity could be small but appreciable. Generally for copper or sodium or metals of this kind at room temperature, it could be of the order of millimeters per second. In pure samples, it could even be larger, centimeters per second, or even meters per second in pure samples, especially if the temperature is small. So the velocity that we consider here, the uncompensated velocity, is really the drift velocity. And when everything is averaged out, so there are electrons moving around and they're scattering off in all random directions, but overall, because of the imposition of electric field, there is a steady drift velocity to the right. And when this steady state condition has been achieved, I can put the left hand side equal to 0. So in steady state, the left hand side is 0. Suppose I don't have any magnetic field, so my Vd over tau becomes equal to minus E So what I could also do is I could put this m here. So sorry, this is the actual equation. There's an m here. So this has to be multiplied by m force. So m here. This is the equation. So this is the dimensionally correct equation. So this would mean Vd over tau is minus E m. Okay, or Vd, the drift velocity, is minus E tau over m E. Okay, so the drift velocity is proportional to the electric field in steady state conditions. Got it? All right. So now in an experiment, so if you have a solid, so you have a solid, you're in the lab, you want to do a transport measurement, what would you do? What kind of measurement would you do? What kind of apparatus would you connect and to this sample to find out the electrical transport properties? What would you do? What would you measure? नहीं भी तो magnetic field कोई नहीं है हमारे पास. What property will you measure? Conductivity or resistance or resistivity. So how will you measure that? वोल्ट मीटर लगाएंगे और क्या लगाएंगे? चलो वो वोल्ट मीटर लगाएंगे लेकिन वोल्टेज मेजर करेंगे और क्या लगाएंगे? सिर्फ वोल्टेज खुद से ही आ जाएगी. इलेक्ट्रिक फील्ड कैसे अप्लाई करेंगे? हाँ, तो इलेक्ट्रिक फील्ड, यू नीड इलेक्ट्रिक फील्ड. सो हाउ विल यू अप्लाई एन इलेक्ट्रिक फील्ड? इलेक्ट्रोमैग्नेटिज्म नहीं पड़ी हुई बिल्कुल. इलेक्ट्रिक फील्ड कैसे अप्लाई करेंगे इस सॉलिड में? हैं? कैसे करते हैं पोटेंशियल डिफरेंस? वोल्टेज कैसे अप्लाई करते हैं? कोई बैटरी लगाएंगे ना, कोई इलेक्ट्रिक सोर्स लगाएंगे, कोई ईएमएफ देंगे उसको, कोई बैटरी लगाएंगे, कोई उसको पावर सोर्स देंगे. सो यू कनेक्ट some voltage to this, right? Some battery, some cell. Suppose that voltage is V. What would you do next? How will you measure the resistivity or resistance? ओम मीटर चलो अभी याद नहीं हुआ. तो वोल्टेज तो मेजर कर लिया, अब करंट कैसे करेंगे? एमीटर लगाएंगे. सो यू विल मेजर द करंट. So this measures the current I. So from the voltage and the current, what would you do? Simple, right? So what is this relationship called? Ohm's law. Okay. So V equals IR is the Ohm's law. So this is what you do in a lab. This relationship connects the drift velocity to the electric field. So can I connect the voltage to the electric field inside this sample? Suppose this length is, say, some x. What is the electric field inside the sample? कुछ नहीं पता, अभी वोल्टेज पता और एक्स पता है. First relation with voltage and electric field. So you apply voltage across a material. What's the electric field that is set up inside the material? So if I divide both sides by x, so what is voltage over this distance? So there's a voltage here, there's a potential difference here. That voltage is dropping, it's a constant potential difference. It's a constantly sloping down potential difference. So if this is x equals 0, this is x equals x. At this edge, the voltage is plus V. At this edge, the voltage is 0. The slope of this line is called the electric field. So I divide the voltage by this distance to get the slope. This is my electric field. Now if I is the current that is flowing through this sample. If I want to express I in terms of the current density J, what would that current density look like? What's the relation between I and J? So which A? What is A here? So this area A. So I is J times A R over X. Okay, so this is the electric field. Let me write this in another. J equals R X over A into E. So I can define So this is also the Ohm's law, the Ohm law. This is the Ohm's law as well. This is just another form of Ohm's law. Now, if I want, so the resistance, does the resistance depend upon the size of the sample? Yes. So, but if I want to talk about an intrinsic property, I would talk about resistivity. So, the resistance equals the resistivity into L, or X over A. So, this is the relationship between resistance and resistivity. So this is R, यहाँ पे X इधर है, एक मिनट, R J A और X, ठीक है. So J is R, J equals X, J equals X, A R. Right? So this means that R A over X is resistivity. So this means J equals 1 over the resistivity E. This is also Ohm's law. The 1 over resistivity is generally called the conductivity and denoted by E. Alright? So this is also another form of Ohm's law. And this is a point form of Ohm's law, because this is a field defined at a point. J is also defined at a point. So this is Ohm's law. Now this is starting to look something similar to this. What I need to do is, now I need to just find the connection between the drift velocity and the current density. I can also put a minus sign here to take into account that this is negative here, and put vectors on top of this. Now what's the relationship between J and the drift velocity? That's very simple. The relationship between J and drift velocity is minus n, the charge density, E Vd. This is something that you already know from basic physics, your electricity mechanism course. Current density is charge on a single electron, the volume density, and the drift velocity. Okay? So a kind of tube of electrons is moving with the drift velocity Vd in a particular volume. The number of electrons is, so can you derive this from me? Can you do this on your fingertips? कर सकते हो ना? So if I were to take if this were a small section X, this were A, cross section area A, the number of electrons in this area is NaX. This is the charge inside this area. Correct? Now if I want to find out the current density, I need to find out how much charge flows through time, a particular amount of time, through an area. This would be the charge density. This would be NaX AT. And of course there is this E as well here. Minus E n x over t is just the drift velocity. Okay? So this is a relationship between J and the drift velocity. So if I put this J and the drift velocity here, I will get minus E NVD equals sigma E. correct? So Vd equals minus, but Vd also equals minus E tau over m E. Therefore, minus En minus E tau over m equals sigma, which means that sigma equals n E square tau over m. This is the conductivity of free sea of electrons, okay, and it only depends upon the number density of electrons and the collision time. The resistivity, of course, will be m over n E square tau. Now this is a crude first approximation of what the conductivity is going to look like. So in an experiment, what you would do, you would measure the resistivity. From the resistance, you measure the resistance using a voltmeter, and the ammeter. From the resistance, you measure the resistivity. By looking at the dimension of the sample, you measure the length and the cross-sectional area of the sample. From the resistivity, you can measure conductivity. You know the density of the material. From that, you can, from the valency, you can calculate the number density of electrons. You know E, m. By the way, so far we are assuming that the mass of the electron is the mass of the electron. It might not be the same. It could even be negative in some materials. It could be much larger. Such material in which the mass of the electron is much larger than the actual mass of the electron, these are called heavy fermionic systems. Tau, therefore, so this is a convenient mechanism to determining tau. And this tau, the average time between collisions is really small. It could be of the order of picoseconds. Okay, so this is how you measure the conductivity, and from this you can determine what this relaxation time is going to look like. Another aspect that you need to consider is that if I were to, so I have an electric field is applied to the system. In steady state, some drift velocity for the electrons is set up. So the electrons are moving with a drift velocity Vd. Really, they are moving with Vd plus thermal velocity, but on average, they are moving with a drift velocity Vd. Okay? Now you switch off the electric field. What's going to happen? What's going to happen? Will they keep on moving with the drift velocity Vd? No. What's going to happen? They're going to relax. Their unbiased velocity will now be zero. They'll just come back to the random thermal velocities. The drift will disappear, and it will disappear at a certain rate. So if I plot T and Vd, Vd is some constant. At a time T naught, I switch off the electric field. This drift velocity is now going to droop down to zero. Which equation or which mathematical equation will help me determine this time? Exactly this equation. So these two terms are zero, dv over dt minus v over tau. So this is an exponential decay in the velocity. So the solution will be v at time t naught e minus t over tau. So the relaxation time, the time constant for this decay, this relaxation will be tau. So the drift velocity of these carriers will go down. Okay, so these are the very basics. one more thing I would like to, any questions about this point? So we're just looking at the classical flow of electrons inside a solid material. Any questions? So if I have experimental measurement that is normally done. So in the Hall effect, if I take the same solid, let's take the same solid I have over there. Now what I do is, there's some current density. Let's call this axis my x-axis, let's call this axis my z-axis, and let's call this my y. Inside, let's call it y-axis, okay? Now there is some current density along the x direction, jx, which of course is given by now some charge carriers, positive or negative, okay? So could be electrons, could be anything else. So this current density, its magnitude is n, some q, instead of E I'm going to write q, Vd, and it's long x. So this current density is actually due to some electric field. So there has to be an electric field here, Ex, and this Jx is really sigma Ex, where sigma is the conductivity along the x direction, field along x and conductivity along x. So far we're keeping things simple. We are making these conductivities and these resistivities as scalar numbers. We are assuming that the material is isotropic. You apply a field along x, the current density is along x. Okay? In reality, solids, due to the crystal structure, they are anisotropic. So sigma and rho become tensors. But we're not kind of going into this for the moment. So there is some current density along x because we've applied an electric field. Now what's going to happen is, suppose I also have a field along the z direction, B, magnetic field, B naught, along the z direction. So my B is along the z direction. So what's going to happen to, what kind of force is going to, if I look at this equation over here, in steady state, everything suppose now is in steady state, I have Lorentz force is going to act in steady state, QE plus Q V cross B equals 0. No force is acting. Both of these forces are oriented such that steady state is achieved. So the left hand side is 0. There is no scattering at the moment. We're not assuming any scattering. This is the condition that we're going to have. Okay. Now you take B and this velocity V along x. There is going to be so this velocity, suppose it has an x component and a y component. You need to solve this equation. So this is probably as a homework. So but what's going to happen is that this magnetic field is going to, since these are charged carriers, it's going to apply a Lorentz force onto the electrons. So the Lorentz force will shift these charges in the negative y direction. So charges will kind of accumulate here. Charge q will accumulate here because of the Lorentz force. So when this happens, suppose these are positive charges, a positive charge will develop on this plate, on this side lateral edge. That will create another field, which is now an electric field because positive charges have been accumulated on this lateral side. So a field Ey develops. And this Ey keeps on growing until more and more charge is developed. So now when charges develop on this side, so a force due to the motion of the electrons is pushing the charges in the direction of this pink arrow, and the electric field is accumulating in the opposite direction. So at one point the two forces cancel out, and this is when steady state is achieved. So when this balance has been achieved, the two electric fields, one is the electric field Ey due to the accumulation of charges. This electric field balances out the force on the electrons, and the force on the electrons is simply this speed Vx B naught, and you need to, so this is a force, you need to divide this by Q as well. So this is the electric field created because of the accumulation of charges, and this is the electric field, the impact of the Lorentz force. So this is Lorentz force, and this is the force that is created by the accumulation of charges. Got it? So this electric field which is created is called the Hall field, and this Hall field must be equal to some voltage between these two sides of the sample. So if I place, since it's a voltage, if I place a sensitive voltmeter here, I will be able to register a voltage. That voltage is called the Hall voltage, VH. That voltage must, so this electric field must equal VH. Let's suppose these dimensions is, this dimension is delta Y, VH over delta Y. Right? So this means that a Hall voltage is developed which equals VB B naught Q delta Y. Now this this is the drift velocity VD. This is the drift velocity for the electrons because of this field. This drift velocity, I can replace this drift velocity with a current density. So if I am able to do that, because in experiments I measure currents and current densities, I rarely measure the velocities of charge carriers directly. So let's express this Hall voltage in terms of current density. So B naught electric field, delta Y is the dimension, Q is the charge, VD is now given by Jx over NQ. Okay. Now what is Jx? Jx is a current into the area. So B naught delta y, some current over this cross sectional area delta y into the length of this sample along x, delta x, n q star. Okay. So this is just the cross sectional area of this material. But depending upon the strength of this magnetic field, a Hall voltage is developed. Okay. So so this is the mechanism of the Hall effect. So if somehow you know the parameters of this material, if you were to measure the Hall voltage, you can tell what the magnetic field is. That's why these materials, through the Hall effect, can measure the magnetic fields. These Hall sensors act as magnetometers. They measure the magnetic field. So all of this is classical at the moment. We've only looked at classical conduction from a totally classical perspective. Now what we would like to do in the next lecture is to see how the Fermi-Dirac picture for these sea of electrons that are enclosed inside a Fermi sphere with these quantized levels, how does it change? And what does electrical conduction mean in that picture? And what does thermal conduction mean? Because not only are these electrons transporting electric current, they are also transporting thermal energy from one end to the other. So if there is a temperature gradient across this metal, there will be thermal conduction as well. So just like we have defined electrical conductivity, there is thermal conductivity as well. So lots of subtle effects can be seen in light of the Fermi gas model for electrons. So today we just looked at conduction from a purely classical perspective. And another important, so when you do condensed matter physics, especially in the laboratory, so in 90% of the cases, the first thing that you will measure is a temperature dependent response. So you'll change the temperature and find out how a property changes. So we're looking at transport. We want to change the temperature and see how the resistance changes, how the resistivity changes. And we know that there is a huge class of material. Just to give you an example, a huge class of materials. Generally, in a very naive sense, this is my temperature, this is my conductivity. I have materials of this kind. Insulators and metals at high temperature behave like this. The temperature goes up, resistance goes up. I have materials of this kind. So can you give me an example of a material that shows behavior like this? Come on. अभी कंडेंस्ड मैटर बहुत कमज़ोर है मटेरियल्स के नॉलेज. कौन सा मटेरियल ऐसे बिहेव करेगा? नहीं मटेरियल कौन सा होगा जो इस the semiconductor. For a semiconductor in the extrinsic region, it will behave like this, right? So and you can get more complicated responses of this kind in a semiconductor in different temperatures. Very low temperatures you have the ionization regime, then you have the extrinsic regime, you have the intrinsic regime. So all kinds of complex behaviors can be seen. What about this material? Which material shows something of this kind? It's an insulator like this, and all of a sudden it just drops to zero. Just drops, not to a small minute number, it drops to zero. It's called a superconductor. So what we can expect to do in this course is we can expect just to describe this behavior for metals. For insulators, it's even more complicated. So for metals, generally we have a behavior of this kind. At low temperatures, close to 0 Kelvin, the resistivity kind of latches on to some base value, it doesn't go to 0. And this is because of the presence of impurities inside the sample. So this resistivity is purely due to impurities. It's called the residual resistivity. This value is called the residual resistivity. If I make a sample which is purer, acknowledge, do that, for metal which is pure, which has a very low defect density, then I can achieve lower and lower residual resistivities. But then there's a temperature dependent response. We need to explain this temperature dependent response for metals, and that we would like to do in light of the Fermi gas model that we've been talking about for these free electrons. In fact, in the middle there is a more delicate balance between rho and T. So this, in the middle, there could be a dependence to the 5th power of temperature. We would like to explain that as well. So only if we are able to understand how the resistivity of a material changes with temperature, which is what most of the times you would do in a laboratory. And whenever a new compound, a new material, a new superconductor, or a new semiconductor, new material is discovered, the first thing you would do is you measure the resistivity versus the temperature in a particular temperature range. Okay, so let's put this off till the next class on Tuesday. One more homework is being prepared.